Good morning and welcome to this next lecture on sound and structural vibration. The current topic we are looking at is the structural acoustic waveguide. And we are trying to derive the coupled waves. Using asymptotic method. So we just last time looked at the flexural wave. We looked at the coupled flexural wave. And we derived a correction. We will get back to that. The next coupled wave we are interested is the coupled plane wave. Coupled plane wave. Okay. So the original plane wave had the wave number omega. The uncoupled had the wave number omega. Okay, so it's a straight line in the plane, wave number plane. So now to derive the coupled wave number, I use this expansion xi is equal to omega plus again a1 times epsilon. I can use higher order corrections like a2 epsilon square etc., but for demonstration purpose this is adequate. Okay. So now to remind ourselves, we have this dispersion equation which we should not forget. This will remain with us for this whole topic. Tan of lambda square root of omega square minus I square plus epsilon. So we have to substitute that approximation in each of these terms here is equal to 0. Okay. So let us look at, we have to look at the plane wave term. So this is 1, and so permanently let us remember this is the flexural wave, this is the plane wave, these are the cotons. So let us look at substitution in the plane wave. Okay. So we need xi square which is equal to omega square plus twice a1 epsilon omega plus a1 square epsilon square. Okay. Therefore lambda square root of omega square minus xi square looks like lambda square root of omega square minus omega square plus twice a1 epsilon omega plus a1 square epsilon square. So this cancels out and I am left with lambda square root of this term. Now I will shorten my derivation. We are looking at the biggest term here. Epsilon square is a very small term compared to epsilon, so I will take it as minus twice a1 epsilon omega. Okay, I will ignore the square term. So that is the plane wave. Okay. Second term. What about the first first has xi to the power fourth. Okay, so let's see, xi to the power square first is omega square plus twice a1 epsilon omega plus a1 square epsilon square. Then this to the power squared is this whole squared. Okay, so that turns out to be, to the relevant terms that I need, omega to the power fourth plus this into twice, which is 4 a1 epsilon omega cube. Okay, and let's say these two, which is plus 4, plus twice a1 square epsilon square omega square. All others are higher order in epsilon. Okay, so xi 4 divided by omega square minus 1 gives me the dominant, or rather terms with smallest order of epsilon values, plus terms in higher order of epsilon divided by omega square minus 1. Okay, so this now gives me omega square plus 4 a1 epsilon omega plus twice a1 square epsilon square etc. minus 1. Okay, now again we take the dominant term, so these are small compared to this and this order 1 terms, so these can be ignored. So this effectively is omega square minus 1. Okay, so that is 1. Now the tan term has the same thing inside as this. Okay, so let me write it here, term 3. Okay, the tan has lambda square root of minus twice a1 epsilon omega. Okay, so tan for small values is small value because numerator is sine, right? Tan is sine by cos. So for small values of this, sine is the argument itself and cos is 1. So we know this is going to be just the argument. So let's put these together. So if I put it together, I have omega square minus 1, the flexural part, then lambda square root of minus twice a1 epsilon omega, then again lambda square root of minus twice a1 epsilon omega. This is the tan term, plus epsilon equal to 0. So I can combine these two together, and I get omega square minus 1 lambda square into minus twice a1 epsilon omega plus epsilon is equal to 0. So now this can be balanced. There are two terms with epsilon value. So if we balance, I will get a1 is equal to 1 by twice omega lambda square omega square minus 1. So now what is the total coupled wave? Okay, coupled plane wave is given by original plus the correction plus a1 into epsilon, right. So 1 by twice omega lambda square into omega square minus 1 into epsilon. So numerator is epsilon. Okay. So just to show you what is happening, I will do the uncoupled waves in a very light dotted manner. Okay. So this is the uncoupled acoustic plane wave. Then this is the uncoupled flexural wave. Then these are the rigid duct cut-ons. This is the second rigid duct cut-on. So now we have done the flexural wave and the plane wave, right. So the flexural wave also had a two-way description, plus and minus. So this is my coincidence, you should know that by now. This is my coincidence frequency omega c, or in the non-dimensional terms omega equal to 1. Omega equal to 1. So the flexural wave first, below coincidence it looks like this. Okay. And above coincidence it looks like this. It has, there is a point where it crosses. There is a point where it crosses the uncoupled wave. It is below, before that point, it is above, beyond that point. Okay. Similarly here also again there is another point it crosses, and below it is lower, above it's higher. Okay. Now a point that should be mentioned here is that again we have three terms, the flexural term which is 1 multiplied by the plane wave term which is 2 multiplied by the cut-ons which is 3 plus epsilon, okay, equal to 0. Now the coupled wave, I will write it here, the coupled wave numbers, cannot, okay, cannot in general cross the uncoupled lines. This is a rule. They cannot cross the uncoupled lines. So what am I trying to say? What I am trying to say is that this coupled line, this coupled solution that I am trying to find this coupled solution, for example the flexural wave cannot go and touch this red dotted line or cross this red dotted line, okay. But it is doing so here, that reason I will give you later. At just one point it is doing, I will give that reason later, but otherwise it cannot. The reason is that when this uncoupled line, for example, is this solution, so this exactly goes to 0 on the coupled uncoupled line, this term. If I land on this flexural curve, uncoupled flexural curve, first number 1 goes to 0. If number 1 goes to 0, you can, there is a balance epsilon sitting here which cannot be balanced. Similarly, number 2 is a uncoupled plane wave. So if my solution exactly lands on the plane wave here or here, let us say, then number 2 is 0, exactly 0, then there is this epsilon which cannot be balanced. So the new solutions in general cannot cross the old solutions, okay. But there are critical points where they do so. We will look at the critical points. There are critical points on the diagram where crossing occurs. We will look at those, okay. Now the third one, the third solution is where tan of lambda square root of omega square minus xi square goes to 0, okay, which means lambda square root of omega square minus xi square is equal to some n pi, okay, or my xi square is equal to omega square minus n pi by lambda whole square for some values of n going from 1, 2, etc. That means the first fellow, first coupled rigid duct cut on, let me call it n1, is given by omega square minus, okay, pi square by lambda square, or xi is the square root of that, xi is the square root of that, xi is the square root of that, okay. Now I will show you. See, these are cumbersome to do by hand, okay. These calculations that I am showing here, still they are probably manageable, but in order to do them by hand is cumbersome, and the geometry is simple, but geometry gets complicated, these terms are all complicated. So we actually use a software called Maple, okay. So I will show you calculations on Maple, how to do these, okay. So let me show you those. Okay. So let us see. This is a Maple sheet I am showing you. The formulas are already there, you can see, okay. So starting is using a restart command, that means everything is reset to 0, okay. So let me run it, restart. Then I have set up the equation which is xi fourth over omega square minus 1 into lambda into square root of omega square minus xi square into tan of the same term plus epsilon, okay. So if I type return, I get that equation, okay. Now I am trying to look at the plane wave, coupled plane wave. So I have a trial solution omega plus a1 into epsilon, okay. Now that trial solution has to be substituted, okay. So as I show you, you can learn Maple commands also. So one is I am going to substitute, which is the subs command, xi is equal to trial in equation. So equation is given above, okay, and I am saying simplify it. okay, because there are fourth powers and so forth, simplify the equation. Okay. Then what I do, these are maple system things that you have to do, otherwise it does not work. So now I am going to expand in a Fourier series the resulting equation. I am going to expand in a Fourier series, okay, about what, about epsilon equal to 0, okay. So that this equation trial is going to be expanded in a Fourier Taylor series, not Fourier series, my apologies, Taylor series around epsilon equal to 0 up till 2 terms, that is what this says, okay. And there is further a little bit of adjustment you have to do. I use a command convert whatever is the resultant as a polynomial, okay. Otherwise it adds the higher order terms as order epsilon square and cube, which cannot be dealt with. So this command will remove the extra terms, okay. Then what I do is, out of that resulted equation I collect that particular equation which is coefficient of epsilon to the power 1, because that is the one I have to balance, okay. So let me run this command. Okay, so I have already run it. So you can see, I will take you the, so I will take you. So this is the first substitution, it looks horrendous. Then what I do, I make a series of it, okay, till to just 2 terms. So I get this term, and you can see it is telling me there are higher order terms, okay. I need to remove this higher order term. So the next one removes that, okay. So it does the polynom command, it removes that, okay. Now within, there is only one term fortunately here, because I have expanded to only 2 terms and I removed the higher order term. Then I collect the equation which is coefficient of just epsilon to the power 1, which is this, okay, which is this. Now I have to solve it for A1, okay, because that is the correction term. So now I solve it and I get the, this is the correction term, okay. So what is the total new coupled wave? It is given by the total, and AC means acoustics, acoustic wave number. So this is the original omega plus this correction term. So you can, this is what I derived on the tablet also, okay. So that is the acoustic wave correction. Now we will do the correction for the flexural wave, okay. So here I am taking the flexural wave correction, which is omega to the power half plus again A1 into epsilon. So I get this, and I go through the same set here, substitute this into the original equation, make a Taylor series, collect the coefficient of epsilon to the power 1, and I get this, okay. See, this is a simple geometry, yet it looks quite complicated. So then I solve for A1, okay, that is the solution. Then I add it to the original, that is my total correction, I mean total new wave number, FL implies flexural, and this is what it is, okay. Now I am going to plot this, okay. So I am going to plot the, I will select epsilon 0.25 and lambda say 3.0, and there is a plotting command, I plot it, and that is how it looks. Let me try to raise the size. Okay. So now let us see this. So the blue dotted line and the green dotted or dashed line are uncoupled waves, okay. Let me say this, that uncoupled implies when there is flexure, when there is a plate, there is no fluid, and when there is a plane wave, the plate is rigid. So, when one medium is there, the other medium is not there. Okay. So, it is kind of in some way incorrect to draw these two pictures together, because when the plane wave is there, the plate is not vibrating, and when the plate is vibrating, there is no acoustic fluid. Okay. That is what is meant by uncoupled, but these lines together give us markers. Okay. So, now on top of that we plot the coupled curves. Okay. So, this black line is the coupled flexure, you can see it is gone above. Okay. In this region, this is the coincidence line, below it is gone above, and as it approaches coincidence it starts to blow up. Okay. So, the actual solution does not blow up, our method is inadequate. The expansion we have used, omega to the power half plus a1 epsilon, that expansion is inadequate, and so the result is not correct, a1 value is not correct. The actual solution does not blow up. If we do it numerically, it will come out right. So, what that means is we have to watch, and at certain regions we have to find a new expansion. So, we will do a patchwork of expansions. Okay. So, this is one critical point where the solution blows up, a1 value blows up. So, we do not take the value till there. So, the flexural correction is this black line. Okay. Further, the next flexural correction, as you saw, the cot term starts to oscillate. Okay. So, close to this flexural curve is again this black line. So, there is a point where it crosses, is another critical point. So, now just before that point the wave number is below the flexure, just above the value is above the flexural wave, and this repeatedly continues, and between every two rigid catons there is one point like that where the crossing will occur. So, that is the flexural wave. Okay. Next we have look at the plane wave. The blue dotted line is the uncoupled plane wave, and the correction to it below coincidence is below. Okay. And then above coincidence it is just above. Okay. That is the plane wave correction term. Okay. We can now let us see if we can do it over here. Let me try this on the fly. Okay. So, I will say that trial is equal to square root of omega square, sorry, that is why I have it written down, so that there is no this is now sorry, okay. Okay, this is now my first rigid caton. Okay, then I do a correction for it, plus a1 star epsilon. Okay, so I will have to start from the top because it is taking the lambda values. So I'll just start. See, the lambda epsilon values were defined, and so it's taking the values which at this point I want them to be symbols. Just okay. Okay. So now we go through equation underscore trial is equal to simplify, substitute xi is equal to trial in equation close this, then equation trial is equal to series equation trial epsilon, two terms, and I will say polynomial. So I am doing it in one shot. Convert. Let's see if this works. And we'll also say that equation, let's see, 3 is equal to coefficient of equation trial epsilon 1. Let's see if it works. Okay, it seems to work, hopefully. Okay, so now let's try and plot this. Well, we still have to solve it, of course. We still have to solve this thing, okay. So let's, okay, let's solve it, okay. So we'll call it solution 3 is equal to solve equation 3 for A1. Let's see if it works. I don't know if it worked, okay. Let's plot and see. Multiple plots. So we have to do here is that solution cut on is equal to square root of omega at 2 minus pi at 2 slash So let's plot. So this happens to be the solution cut on correction. Let's plot if it works. Okay. So I'll copy this. Solution cut on, and we'll give it a color. What color will we give it? Let's give it blue. Let's give it blue. We got the curve right, I think. Time is up and we will explain it in the next class.